right, so this is our video for our fusion notes. And so you should have your fusion notes print out and to take those, and I'll help you out as we go. You will need some colored pencils or pens, so make sure you at least have 2 different colors. All right, here we go. All right, so some key terms that we're going to talk about here in fusion. The first one is, of course, fusion, what it is, how it happens. Isotopes, we've talked a little bit about isotopes, we reviewed isotopes, and so we'll be using those nuclear notations here. And then a nuclear equation. I'm going to explain what is a nuclear equation and how it works. All right, here we go. So for step 1, in your notes, you're right that there is a collision. This box here is what you're going to draw into that box for step 1. So you're going to label this. So pick one color for protons, one color for neutrons. And once you draw this and you name it, this is deuterium, and it is hydrogen 2. Okay, so H and a mass of 2 and a protons of 1, or atomic number of 1. And it collides with tritium. And there is 1 proton in tritium here for atomic number and 2 neutrons because there's a mass of 3. So this is the main part of what should be in your box for your image. Okay, so you can pause the video right now. Make sure you're drawing this in and using 1 color for protons and 1 color for neutrons. I will be looking for color. All right, so fusion starts when deuterium and tritium, which are isotopes of hydrogen, smash together. So these will collide together. A reaction always happens with the first thing that happens is a collision between 2 atoms. So that is the first step here in fusion. And it is deuterium and tritium, which are usually what causes the collision. So when we talk about fusion, a lot of times we talk about these 2 isotopes of hydrogen colliding. There are other small atoms. Notice these are very tiny nucleus or nuclei, and they are small. So fusion starts with 2 very small atoms colliding. All right, step 2 is the actual reaction. So again, this is what you're going to draw inside your box there for step 2 and write reaction. So the reaction is that the 2 small, hydrogen isotopes collide with each other to make 1 big helium. And notice there's these lines here. These lines are showing that this is very unstable and it's shaking, which means it's not going to stay together. And that's what neutrons do. When you get too many neutrons, it becomes very unstable. And I'll show you what happens. So draw this into your box for your image for this one. Make sure you're using consistently the color for protons and neutrons. And this reaction actually makes helium, but this reaction is a large amount of heat and pressure. So this does happen under the earth where there's a lot of heat and pressure. Of course, we know, right? The core is really hot, and there's a lot of pressure down there. This also happens, that's how it happens on Earth to make the helium. In a minute, you'll see the helium that you love to put in the balloons to make them float. But the main thing this happens in is the sun. So this is how the sun makes energy. And you'll see in a minute what comes out. So this is the intermediate. This is what happens before we get our product. So we get our 2 reactants here. Our 2 isotopes of hydrogen collide and combine into a larger helium atom. Okay. Now step 3. So step 3 is that energy comes out. So this is on the other side. We've had them collide. They've combined into this large helium atom. 2 smaller ones combined into 1 big one. And what happens is because it's unstable, now it's going to split apart. And so this reaction creates a regular helium atom. Notice there's no shaking or energy left in there, so it's very stable. Has a mass of 4, atomic number of 2. This is helium. Now, this is the helium that you actually put into your balloons, okay? And also what comes out is a neutron. So neutrons, as we know, are included in our atomic mass, so it has a mass of 1. This down here, we call its charge. And it has no protons in it, right? Because this would be atomic number. So neutron is not an element. So it has an atomic number, a charge of 0, atomic number of 0, has no protons. And this is how we write the nuclear notation for a neutron. So what comes out is a helium atom, helium isotope, and a neutron, okay? And then what also comes out is a ton of energy. So this fusion reaction makes 800 million eVolts. Your barbecue makes 50 eVolts, remember, from the fission. So this makes 100 million. And if you remember from the fission, if you did the fission first, that made 200 million. Well, this is 4 times the energy. So this is a lot. And this is actually something they're looking into currently about making power, because it's going to release a lot of energy. And so how can we make power? They've actually been able to do one fusion reaction up in Livermore Laboratories, which is up near Stanford here in California. I think they did it now 2 years ago. So now their idea is, how can we do this without using a lot of energy, but to produce a lot of energy and make it safe? Because they're looking at maybe this would be our next big energy producer to make the power to run our homes. All right, step 4. So step 4 is that talk about conservation of mass. So conservation of mass and matter is really, really important. So every chemical equation and everything in chemistry has to follow this. We cannot get rid of or create new protons, neutrons, and electrons. Excuse me. Okay? What we have started with here on the earth is all we have. We cannot make new ones. So they have to show up. So in your notes, you're going to have 2 sets of boxes. The first one says picture. And this is what's going to go in that picture side. So right under that word picture, you're going to draw this image right here. You're going to draw 1 proton, and make sure you have a legend somewhere around there to tell you what color is proton, what color is neutrons. You're going to put 1 proton and 2 neutrons. You're going to draw it just like this. And then underneath it says nuclear equation. This is what you're going to write right underneath those words of nuclear equation. You're going to write a 3, a 1, and hydrogen. Okay? And then you have 5 boxes. So this is for the picture boxes. This is the first box, second box, third box, fourth box, fifth box. For the nuclear equation boxes, this is your first box, your second box, your third box, your fourth box, and your fifth box. Okay? So pause it right now and make sure you have those in your boxes. All right, now that you have those done, now what we're going to do is look and see how this proves conservation of mass. So conservation of mass. So what we start with, which is on the left side of our reactants, we must end with our products. So if we look here, we have a mass of 3 here in this atom and a mass of 2. So we're going to add these together. So 3 plus 2 gives me a total mass of 5, which means if I'm starting with a mass of 5, okay, of protons and neutrons, I must end with a mass of 5, because that means I'm conserving or still keeping the protons and neutrons. So I'm only going to add the mass numbers together. So this is 3 plus 2 is 5. These numbers on this side should also add to 5. So 4 plus 1 also gets me 5. Notice the mass is conserved. We started with a mass of 5. We ended with a mass of 5. Okay. The other thing is the conservation of matter. Now, matter here in chemistry is protons, neutrons, electrons, okay? Which means we are really more paying attention to that conservation of protons. Neutrons were definitely conserved as well as protons, because that's what makes up our mass, but let's check our conservation of protons. Okay, so we started with 1 proton here, plus 1 proton here, because these are my atomic numbers, which tells me the number of protons. So I start with 2. So this side over here should also have 2. So 2 plus 0 also gives me 2. So not only is our mass conserved, but also our matter is conserved as well as our protons. Okay? All right. So now what I want you to do is take a second, and I want you to look at those last 2 questions there on your notes and try to answer them. Just pause it right now, try to answer them, and then you'll get the answers in the next slide. All right. In our overall, you don't have to draw this out. This is our overall reaction. So in fusion. We have two small atoms, a hydrogen and hydrogen 2 and a hydrogen 3. Remember, this is on the top of our periodic table because we learned the trend is our smaller atoms are on the top. They will collide together to make a larger helium, okay, atom, which has a mass of 5.2, okay, and it is very unstable, so it will eventually split out, has a lot of energy, so that energy will come out because remember, we also have to conserve energy. As we learned last semester, if energy goes in, something has to go out. The energy has to go somewhere, okay? And notice it also makes a helium, helium 4 atom, and a neutron, okay? Also think about, because we have to remember when we learned about endothermic and exothermic, okay? And I'm going to go back one slide to look at this one. Now, looking at this, we can determine if this is endothermic or exothermic. Remember, endothermic means that energy is going into the reaction. And we learn if it's going into the reaction, it's going to be in the reactant side. It's part of the reactant side because it's going in to make the reaction happen. But this one has energy coming out. Now, remember, if it comes out, then that's that exothermic. And the reason we can feel it and it's going to feel hot is because it is releasing that heat and energy and it's coming out. So this is very hot, which we can kind of imagine because this happens in the sun and we feel the heat from the sun, okay? So fusion is an exothermic reaction, okay? All right, so here's helping us answer these two questions. So what two isotopes are used to start fusion? Well, hopefully we have answer number 1, lithium and electrons, deuterium, tritium, helium, and neutrons. Hopefully you wrote down deuterium and tritium. These are the two isotopes, or you could have wrote H2 and H3. Okay, good. All right, and then which reaction produces the most energy by mass? Hopefully, now that you did the fission and you heard that, it is fusion. So fusion produces, remember, 800 million eVolts. Well, fission is only 200 million eVolts, okay? All right, so go ahead and put those notes into your notebook. For the page numbers, you can look it up in Classroom. If you have any questions, please let me know.